Hello everyone, I am Dr. R.C.S. Chauhan, Associate Professor, EC, IIT Lucknow. I will teach the subject Communication Engineering, KEC 401. This is the first lecture, and in this lecture we will discuss basic introduction of signals and system for communication engineering. In this subject, this is the syllabus. In first unit, we will review the basics of signal systems, frequency domain representation of signals, principles of amplitude modulation systems, demodulation, and in amplitude modulation DSB, SSB, VSB modulation and demodulations. In unit second, we will discuss basic about analog modulation, in which angle modulation, representation of frequency modulation, phase modulation signals, and spectral characteristics of angle modulated signals. In unit 3, we will discuss basically about random processes, then review probability and random processes, different noises, Gaussian and white noise, their characteristics, and noise in amplitude modulation systems, noise in frequency modulation systems, pre-embedded pre-emphasis and de-emphasis threshold effect in angle modulation. In unit 4, we will discuss about pulse modulations and different type of pulse modulation and sampling process, sampling and then pulse amplitude modulation, then pulse code modulation, differential pulse code modulation, delta modulation, etc. and in noise also in there, and time division multiplexing and digital multiplexers. In unit 5, last unit, we will discuss basically the digital modulation schemes, amplitude shift keying, phase shift keying, frequency shift keying, and quadrature amplitude modulation. Their demodulation schemes also along with the continuous phase modulation and minimum shift keying. This is the syllabus which we will cover in all 5 units. Okay. Now, first is the introduction to communication engineering. See, basics of communication system as transmitter, channel and receiver. Then in communication, basically there is a source which provide the signal, message, information, and it to the transmitter section. Transmitter section basically modulate the signals at high frequency, high amplitude, with high amplitude signals transmitted to the channel or medium that may be wireless or wired, and through that channel the signal is received at the receiver part, okay, along with the destination. At the receiver, the signal is demodulated, decoded, and that demodulation decoding requires same carrier as used in the at the transmitter section for modulation, and that demodulation, after demodulation process, decoding and etc., and it goes to the destination part. Here we can draw, it may be a transmitter section, then channel, and then passes to the receiver section. Okay. And in basically when the source is there is a source also, and at the receiver there is a destination. Okay. The source may be analog or digital. If it is analog and we want to transmit the signal in analog mode, then there is a analog modulation used at the transmitter section. This analog modulation done with a high frequency carrier with high amplitude, and that carrier goes with the signal and to the channel, and at the channel some noise may be added, here, to the channel, and that noise may some errors can be introduced in the signal, and that error is reduced at the receiver section basically, and demodulation also the reverse process as done in the transmitter section, and then goes to the destination. For example, I am communicating with you, and here I am providing there is an analog signal as a audio signal, and my pictures and video as a video signal, and both are analog signal. Those analog signals can be transmitted from the source to the transmitter section. Firstly it is modulated, then passes to the channel where noise is added, and that signal passes to the receiver at your end, and that at that end it is demodulated, okay, and decoded if encoder process done at the transmitter section, then goes to the destination. Okay. This is very basic of the communication engineering. Okay. Now, next is the system with the impulse response. See, in any block which is passing some signals, suppose signal is the analog signal xt, and at the output of the block we are getting output yt, then this block can be characterized with its impulse response of the system ht. This ht is nothing but when xt is impulse signal delta t, then its output yt equals to ht. Then when impulse signal input to the one block or system, analog system, okay, then it whatever output it provides, that is the impulse response for the signal input signal, impulse signal. Okay. Then that impulse response become the characteristics of that system. It is a analog system. Okay. And delta t, as we know that delta t is the impulse signal, its value is 1 at t is equal to 0 and 0 otherwise. Okay. This is the delta t. Okay. And some other known signals, that is this is the unit impulse, similarly unit step ut, okay, its value is 1 for t greater than 0, its value is ut is equal to 1 for t greater than equal to 0 and 0 for t less than 0, then it is 0 for t less than 0 up to minus infinite. Okay. Other signals, basic signals, next is the ramp signal RT, its value is 1, its value is RT is equal to TUT, RT is equal to TUT. Okay. This value is equals to, suppose this is the t axis, then its value equals to t, okay, and 0 in the negative region. Okay. It is 0 for t less than 0, okay, and t greater than equal to 0. It is not equality here. Okay. Then these are the basic signals which can through these basic signals the analog signals can be combined, and these analog signals passes to the analog system to get the output yt. Okay. These output yt can be computed with the help of input xt and the impulse response ht. Yt, as we have discussed in signal system, xt linear convolution with ht, okay, and it can be given as t minus infinite to plus infinite x tau h t minus tau d tau. Okay. This is the output yt. Okay. Now, similarly, this is for analog system. Similarly, for digital system or discrete time system, input is xn, output is yn. Xn is nothing but the sampled version of analog signal xt, whatever the signal xt. If we do some sampling process, we can generate xn, and that xn can passes to the discrete time system, okay. And to get the output yn, yn again nothing but the linear convolution of xn and hn. In equation form it can be written as xk h n minus k minus infinite to plus infinite. In time domain, basically input with the impulse response, linear convolution of input xn with the impulse response hn, we can get output yn. Hn is again nothing but the, for input delta n we can get output hn. Hn is delta n is nothing but the, its value is 1 at n is equal to 0 and 0 otherwise. This is the delta n. Other signal in discrete time domain, that is un, okay. Its value is 1 for n, its value is 1 for n positive and 0 for n negative. Similarly, Rn, okay, okay, nothing but the sampled version of the Rt. This is Rn, okay, Rn, it is given as n times un, okay, and 0 for n negative, okay. Now, in time domain, this input xn, linear convolution of hn, we can get output yn, okay. But in frequency domain, suppose firstly in continuous time yt is equal to, as we have discussed, xt linear convolution with the ht, that is nothing but the integration minus infinite to plus infinite x tau ht minus tau d tau. In frequency domain, its frequency version, that is the y j omega is nothing but the x j omega into h j omega. X j omega is nothing but the frequency domain signal of the xt, h j omega is the frequency domain signal of the ht. Then in frequency domain these signals are multiplied. Similarly, in discrete time the frequency domain signal of the yn, that is the y e to the power j omega is equals to x e to the power j omega into h e to the power j omega, okay. Then I want to say that for any signal in time domain, in continuous time domain or discrete time domain, you know, both signal have their frequency domain signal. For xt we have frequency domain signal x j omega, for xn we have frequency domain signal x e to the power j omega, okay. And types of signal, that is but obvious in continuous time and discrete time as a time domain signal, that we have discussed already, that xt, its sampled version, that is the xn, okay. This is the continuous time signal, this is the discrete time signal, and every these signal have their frequency domain signal x j omega. Xn also have frequency domain signal x e to the power j omega, okay. And how can we find these frequency domain signal corresponding to analog signal or continuous time signal and discrete time signal xn, the frequency version of that x e to the power j omega, that we will discuss in the next slides, okay. Before going in detail of frequency domain signal, we can discuss the block diagram of digital communication system also. Okay. Here as we know that there is a source, this is the transmitter section, it is the receiver section, it is TX transmitter section, it is receiver section. Okay. As in the analog communication I have discussed in the last slide. Okay. Here in digital communication along with the modulation there is a channel encoder and source encoder also incorporated with the transmitter, and to find to do the its reverse process at the receiver section there is a source decoder and channel decoder. Okay. These source encoder and source decoder, basically the information from the source may be analog or discrete maybe, and that converted into a binary part, that binary signal which is the unique, so that it can be decoded uniquely at the source decoder. And at the channel encoder and channel decoder, basically these blocks are used to correct the errors occurred in the channel when this signal passes to the digital modulation, then to the channel, and channel there some noise can be added and which will corrupt the signal and will introduce some error, and with that error it is demodulated, but at the channel decoder we can minimize the number of errors occurred in the channel. Okay. And that source decoder we have discussed already, and only here, that is the digital modulation and digital demodulation, that we will also discuss in the some units. Okay. That is different from the analog modulation. In analog modulation we will use discuss some analog modulation schemes, and in digital modulation we will use the digital modulation schemes. Okay. Now again come to the introduction of communication engineering, and then periodic signals. Okay. Signals are two types, periodic and aperiodic signals. Okay. We will discuss only continuous time signal firstly. Okay. Then we know that any periodic signal xt can be expressed in terms of its Fourier series. Uh, 0 to 0 to, this is not 0, just an adjustment. Xt periodic signal can be expressed as Fourier series k minus infinite to plus infinite ak e to the power j k omega naught t. It is a periodic signal, but this periodic signal can be expressed as a sum of exponential signals with some coefficients ak. Okay. Any periodic signal, this is the its Fourier series, and its Fourier series coefficient ak can be calculated as 1 upon t integral over period t the given xt into e to the power minus j k omega naught t dt. Using this we can find ak. This is the given periodic signal xt. Using this given periodic signal xt we can find ak firstly, and these coefficients ak can be used here in this Fourier series equation. Okay. To find Fourier series of given xt, that is in this term. Okay. And see here the coefficient ak, if you multiply it with t, so t ak equals to integral over t xt e to the power minus j k omega naught t dt. Okay. This we can say this is nothing but the function of x terms of j omega naught k, j omega naught k, this is omega naught k, it is the function of j omega naught k. We can term it as a function of as a x function of j omega naught k. Okay. Now, for periodic this can be given as like this, and for aperiodic signal, now come to the aperiodic signal. The aperiodic signals have there is a, we can say what is the period of the aperiodic signal, then we say that aperiodic signal found with the infinite period, infinite time period. It is assumed that any aperiodic signal, it has infinite time period. Okay. Then aperiodic signal with infinite time period, then t tends to infinite, okay. Then its frequency f is equal to 1 upon t tends to 0, not equals to 0, but tends to 0. Then we can say it is nothing but the df, okay. And 2 pi f, that is omega, it may be f naught, t naught, f naught, this is f naught, then omega naught also tends to 0, that is d omega. Okay. Now, a periodic signal is also a periodic signal, then these equation can be used for a periodic signal with taking period t as a infinite. Okay. Now, this function x j omega naught k, because omega naught tending to 0 and that is nothing but the d omega, then in multiple of the d omega, you know, when we varies the k 0, 1, 2, 3 like that, then this k omega naught becomes omega when k varies from minus infinite to plus infinite, then omega varies from minus infinite to plus infinite. Okay. Now, this equation can be converted into x j omega equals to t infinite, then minus infinite to plus infinite, x t e to the power minus j k omega naught e to the power minus j omega t dt. Okay. This x j omega, okay, this is corresponding to a given signal x t. Okay. We can find x j omega for a given x t. This j omega x j omega is nothing but the Fourier transform of x t. Okay. And basically this is nothing but the t times a k when t tends to infinite. Okay. And we are calculating its coefficient. Here we are using these coefficient to find the Fourier series, okay, in periodic, and similarly we can use this as a coefficient for Fourier series. Okay. Then we can write the equation for x t in terms of a k or x j omega. Okay. That equation we can write here, x t equals to, because summation k minus infinite to plus infinite, it converted into integration for omega, because omega is continuous now, then minus infinite to plus infinite a k, because t a k equals to x j omega naught k, then this is nothing but the t a k. Okay. Then a k is nothing but the x j omega upon t. So, 1 upon t x j omega into e to the power j omega t, and with respect to d omega. Okay. Then this equation represents inverse Fourier transform, of x j omega in terms of x j omega. Okay. Basically this is nothing but the Fourier series for given aperiodic signal x t, but it will be used to compute the inverse Fourier transform, and this equation will be used to compute the Fourier transform of the x t signal. Basically this x j omega nothing but this x j omega nothing but representing the frequency domain signal corresponding to x t. Okay. Then a periodic signal have their Fourier transform, and that is nothing but the frequency domain signal. Similarly, for a given x n, its sampled version we can find its discrete time Fourier transform x e to the power j omega. Okay. That will be the frequency domain signal corresponding to this x n. Okay. Next, energy of signal and power of signal. Okay. See, any signal x t, this is x t at any instant, okay, we can find its instantaneous power by calculating mod of x t square. If x t in voltage or current, then we can find its power mod of x t square, that is the instantaneous power. Okay. This power can be integrated in a given time domain, time range minus t by 2, suppose to up to plus t by 2 mod of x t square dt. Okay. This is nothing but the representing energy of signal in duration minus t by 2 to plus t by 2. Okay. Now, this energy of signal x t in this time minus t by 2 to, suppose this is the up to t by 2. Okay. We can find power of the signal by taking average, okay, that is 1 upon t integral minus t by 2 to plus t by 2 mod of x t whole square dt. It is the average power of the signal in the that duration. Okay. This is the average power and signal. Time is almost going to finish, and in next class we will discuss energy spectral density, power spectral density, and autocorrelation and cross correlation functions. Okay. These are the references we can use to discuss and study about communication engineering. Thank you.